have 4 factorial. So there's ways to get around this. Okay. Now, thinking about no interaction effects of interest, so this is something probably you're familiar with. Okay. So first one is the average treatment combination effect. So this is probably the simplest one, which is the average effect of a particular treatment combination relative to the baseline. So A equal AL, B equal BM. What's the effect of that combination relative to the baseline? Okay. So it's useful when you're asking the question which treatment combination is most efficacious, for example. Now this another quantity that's recently introduced by Jens and Tepe and Dan. This is sort of effect that we built on, and in fact our work basically generalized this to the interaction. They've called this average marginal treatment effect. Okay, so what's that? Well, basically what they're doing is they're looking at the effect of A relative to the baseline condition A 0, but averaging over. Okay, instead of conditioning the B to a particular value, it's averaging over the distribution of another treatment. Okay, so if it's equally likely, if the treatment B is equally likely at each level, you first set it to 1 with 1/3 of probability, and you set it to 2, another 1/3 probability, and then you set it to 3, another 1/3 of probability, and then average that over. Okay, so this makes sense because it allows you to focus on it's a marginal effect, right? When we say marginal effect, and when we run actual regression, right, that's what you get. Coefficient for the main treatment effect, main term, the treatment term, the coefficient for that is a marginal effect. Okay, assuming that treatments are independent across all the treatments. Okay, if there's a dependency, and if you ignore other treatments, you got a problem, right? But if you just take, if A is binary, and if you ignore B, C, D, E, F, whatever, and just do the difference in means, right? That's the marginal effect. You're implicitly averaging over all these other treatments. Okay. So what that means is that if you change the distribution of other treatments, how the other treatments are assigned, your answer is going to change. Okay. So if someone runs experiments, there's say A and B, they choose different treatment probability for factor V, then you get different answer for the effect of A, because you're averaging over in a different way. So this is useful when you ask which treatment is effective on average. Right? But here, on average, meaning average across other treatments. Okay, so that's basically the no-interactive effects. So what about the conventional approach to causal interaction? So that's the interaction term that I showed you earlier. So this is a generalized version. There's a conditional effect interpretation, right? Effect of A when the B is set to something, contrasting that with the effect of A when B is set to another value. And you also have interactive effect interpretation. So this is the average treatment combination effect. Right? It's the effect of this combination AL and BM relative to the baseline A0, B0. But the subtracting the effect of A when the B is set to the baseline, effect of B when the A is set to the baseline. Again, these two interpretations give the same number. It's the same as this. Right? So that's the conventional way of doing it. And how do you estimate these interaction effects? Linear regression with interaction term. Okay, so if you run the linear regression, just like I showed you in the toy example earlier, if you run the linear regression and look at the interaction effect, this is what you get. It's exactly, the unbiased estimate of this. Okay. So, and then you have to think about how you interpret the results, whether it's conditional effect or interactive effect interpretation. Okay. Another thing you might have seen in the literature, if you look at the experimental design literature, is something called interaction plot. Okay? So the interaction plot basically plots all the average potential outcome estimate from your data. So here, just as an illustration, I'm picking from that experiment Jens and et al. Did. So here's the education level. And then each line represents different years of experience. So this is the just an average potential outcome, and I'm ignoring the rest of the factors right now. But this is the average outcome, right? So here is the estimated probability of immigrant being preferred for admission. And this is the, basically this red line, for example, is the someone who have no job experience and how that person's likelihood of being preferred changes as a function of education. Okay? And since there are many levels of experience, you get this crazy lines going back and forth. And from this, you're supposed to say, there's an interaction effect. Yeah. There's a question there.
Why is high school the second?
Oh, yeah. To confuse you even more. Thanks for catching the typo. Thanks for catching either the typo or okay, maybe that's why it looks a little weird. So that's just playing the game in my favor. But good point. All right, so thank you for pointing that out. I'll look into it. So the problem of this interaction, so you see this in the experimental design literature, is that it's not really plotting the interaction effect itself. So you actually have to look at the difference between these and how that difference changes along the x-axis. So when you have many lines, that's kind of hard to do. Right? If you have like two or three lines, maybe it's easy, but it's a little bit hard to do. So I'm just trying to show you that like, interaction plot is not really useful when it gets high dimension. And we're not even that high dimension, there's just two factors. So why not just like report the numbers, right? I mean, that seems like table, right? Old-fashioned way, right? So here, this is just the regression coefficient, estimated regression coefficients from the data. That's the conventional definition of interaction effect. And so here, there's a job experience and education. Oh, now it's placed the right place. Okay. So that was okay. No, intentional. And I highlighted with the gray that the highest interaction effect. So you might say, well, it seems that these three combination gives additional boost. So for example, this gives additional boost beyond being high school educated and having the 3 to 5 years education. Okay, so this is just a toy number. So there's something special about these three. Okay. Now, because I picked these none as a baseline, which in this case seems to be the right thing to do, you get 0 effect on any of these rows. Okay. Now I changed the baseline, and the things change dramatically. So instead I set like highest education and highest job experience as a baseline. Maybe I want to compare with the highest, not the lowest. Okay. Now I highlighted the three highest interaction effect, and it turns out none of this is appearing in this. So in fact, there's lots of zeros are now in a different place. So you can see the problem, right? It's sort of depending on what you pick, you get different answers. Okay. So lack of this is what I mean by lack of invariance, and you can prove formally that the order could change. Okay, so you might think that the word is just an interval, but like as I showed you, it's not just the difference changes. It's order could anything can go basically. So we basically proved that more formally. So interval invariance meaning the difference between two interaction effects should be the same, even if you have different baselines. Order between the two interaction effects should be the same, even though even if you have a different baseline, and those two properties don't hold for the interaction term. Okay, now so the new interaction term that we propose. Okay, so this is again it's an extension of what the Ians and Tepid and Dan proposed to the interaction term. Okay, so here we call average marginal trimming interaction effect. So the only thing that's different is the marginal part. Okay, we're going to use the interactive effect interpretation. So we're going to define the interaction effect as the difference between the trimming combination effect. So this is the effect of trimming combination to the baseline minus the marginal effect of each one. Right? So this is again, it's like, do you have additional bonus effect beyond each of these the effect of each treatment? Right? It's just something special about this combination beyond just being highly educated and having lots of job experience. Okay? So it's basically sticking to the interactive effect interpretation. It's additional effect induced by this combination together beyond the separate effect of each one. And we proved that these are both interval and order invariant. In fact, you don't get zeros on the edges. You get numbers everywhere. And that relative difference between any of these combinations stay exactly the same. Now, the only thing that you're trading off here is that just like the marginal effect, it's going to depend on the distribution of the treatment assignment. So how you assign the treatment, it's going to change your answer. Right? So that's the trade-off. So you're getting this invariance by not conditioning on the baseline. But then your results are not going to rely on the baseline condition, which baseline condition you pick, but your results are going to depend on how you assign the treatment. Okay? So how do we justify that? Well, maybe you can justify by the experimental design that you use, right? To the extent that you can justify your treatment assignment as an experimentalist, maybe you should be able to stick to that. The second possibility is you can motivate this by the target population. So you can think about in the target population how these treatments are distributed, and use that or estimate of that treatment assignment distribution as a way to define the marginal effects.
Okay,
yeah.
Clarification
Sure,
question,
sure.
going back 2 slides.
Oh, sure.
For tables 2 and 3 in the paper,
Yeah.
they're run on exactly the
Yeah,
same
exact
model?
same data.
And so they have the same predicted values?
Yes.
So if we looked at the R-squared, they'd be
Yeah,
identical?
it's an identical model. Yeah.
Because the point, these aren't wrong.
No, it's
They're
not
the
wrong.
correct answers
Right.
to 2 different questions.
Mm-hmm. That's right. So these are not wrong numbers, right? In fact, I'll show you that the new interaction effect is a function of these numbers. So nothing is wrong. It's just different questions, different interpretations. Okay. So basically, what this says is you probably shouldn't be comparing unless you're committing to the baseline, in which case you can do whatever you want. But if you're not be able to justify your choice of baseline condition, you shouldn't be comparing these different interaction term coefficients. Because if you do, then when you change the baseline, the order or difference can be completely different. Yeah.
So just to understand, the predicted values are exactly the same.
Yes.
Just because we're comparing to a different reference group, they're getting different coefficients. But if we plug it into predicted values of each of these cells, in this slide and the previous slide, we're getting the same predicted values?
Right, so each potential outcome, like each treatment combination gets the same predictive value. Right? Now, but the interaction effect is more than that, right?
Why?
Because you're trying to summarize this large number of possible combinations with a fewer number of interaction terms. Right? Because there could be one-way, two-way, three-way, four-way interaction, who knows? Right? But you're trying to understand, right, this complex, like if it's 2 by 2, not a big deal. Right? You can put the 4 numbers. And if with the interaction term, it's just you have 3 numbers instead of 4. Right? You have main effect, 2 main effects, and you have 1 interaction. So you're trying to summarize, 4 numbers, right? 4 combinations with 3 numbers. So there isn't much loss. But when you have many levels and many treatments, the potential number of the number of potential treatment combination is large. But you're trying to summarize that by like which combination is giving you this result.
Maybe I don't understand. So how do you read this 0.138? Isn't that just
Okay. So yeah. So sorry. Yeah. So maybe yeah.
through,
No, so these are not potential, sorry, yeah, so this is not a predictive
something
value.
you hold constant.
Yeah, so this is not a predictive value. This is the coefficient you get
Yeah.
for the dummy between none and 4th. right? So this number 0.065 is a coefficient for the dummy variable being fourth grade and no experience. That coefficient is this number with a standard error.
Yeah, exactly, but my point was like, you can use that to calculate some predicted value of the likelihood for this person that you, I think this is immigration, say you'd meet this person.
Right.
And you would be getting exactly the same predicted
Yeah, so that's
value
this.
in the two different...
Right, that's this. So this is the predictive value
Yeah.
of having no education and no job experience. That's 0.45. Okay, so that's what the interaction prop people, or if there are any people like that, would say. Like, just look at this and read the interaction from here. And I messed up something, but my claim is it's kind of hard to do. Okay. But you might be able to do that. Yeah. But this is like 2-dimensional, right? If you add third dimension, you have to add, smell and right, mushiness, or so you feel interactive there. And, yeah. All right. All right. Sorry. Okay. All right. So where are we? All right. Okay. So basically, this is sort of additional. I mean, again, it's a different question, right? So if the question is not this kind, right? It's not like additional effect, then you shouldn't do this. Okay? And it turns out that this new quantity is a linear function of this other conventional quantity. So what you have to do is you still run the regression, and then you get these coefficients, and then you plug in this formula, and then you get the new quantity. So it's all simple. And it also turns out the other way, so that all conventional quantity is a linear function of this new quantity. So you can go back and forth. Okay. So nothing is wrong. It's just a different interpretation. Yeah.
Can you use the empirical distribution of the treatments?
Right now,
It's
yeah.
not the design-based.
You could use design-based, right? So this, well, if there are empty cells, you can't, I guess.
There'd be nothing to plug in.
Yeah.
Yeah. Okay.
Yeah, so I guess I guess in the end you may end up using. Yeah. Oh well. I have to think about that. Yeah, that's a good question. I mean, in theory, you could plug in any value here. Right? These are probabilities of treatment issues. That's a good question. I have to think about that. So now what you can see from this is the absence of causal interaction, like complete absence, is the same. You get the same basic results, whichever quantity you use. So if the conventional quantity says there's no causal interaction whatsoever, new quantity is going to be 0 too. If the new quantity says there's no interaction, then the conventional quantity is also 0. So F-test, like people do F-test, right? They do any, is there any interaction? They do the F-test on the interaction terms. That's still valid, right? That's just whichever effect you use, because now, under the null of no interaction, two quantities are the same. Okay, so that's basically the core of the paper, and then basically the second half of the paper generalizes these results to the higher order. And one thing I wanted to emphasize is the conventional definition of higher order interaction is a little weird. So just making sure it's not going to order. Okay, and so I wanted to just convey that. Right. So if suppose there's a bunch of treatments, so not just two, right? The two J ways. Okay, and you basically assume the same thing. Let me show you. Okay, so here the conventional higher order interaction is actually defined. If you look at the textbook, this is three-way interaction is defined. Three-way interaction in the conventional approach is defined as difference between two-way interactions when you set the third treatment to a different value. So it's basically conditional effect interpretation. So in a two-way case, it was what's the effect of treatment A when the B is set to different values. Now to go to three-way, they have, what's the difference of the two-way interactions when the third variable is set to the different values, okay? So the problem with this interpretation is that it's a little crazy because this two-way interaction itself is a conditional effect. So it's like a conditional effect of the conditional effects. See what I mean? And if you feel like you're confused, that's the right reaction. So in the higher order interaction, it's very difficult to understand the conditional effect interpretation. So what we do is we basically generalize the new quantity, which is the interactive effect assumption, and that can be easily generalized to higher order because you say, is there something special about this three-way interaction that cannot be accounted for all the one-ways and all the two-ways? Okay. Then that's the three-way interaction. All right, so finally I'm going to go to the example. And I'm going to show you the empirical analysis. So we're going to assume, we look at the 5 factors for these 2 reasons. And they did the match pair conjoint analysis. So you basically, two profiles and person chooses one, which one they like better. And so we're going to randomly pick half of it and then do linear regression. So binary outcome, whether a profile is selected. And we're going to put the model with one-way, two-way, three-way interaction, all of them. And you might say, wait a minute, how do you do that? So this is a p greater than n problem. It's called in biology. So num-p is a number of covariate predictors. Is with one-way, two-way, three-way, it's 1,575. Oops, that was bigger than my sample size. See what I mean? That might be a problem. Like when you can't actually run linear regression. So this is called Causal dimensionality. So one way to approach this is a sparsity assumption. So this assumption says, the world is sparse place. A lot of things are 0. A lot of effects are 0. Only a few of them are non-zero. Okay. So there's a sort of standard method called Russell. Right? Variable selection is Russell. Catch the variables. Okay, all right. That's sort of to the extent statisticians can make themselves fun. Right, so we apply that and then you get like 99 non-zero coefficients and then bunch of coefficients being 0. And you can, so this, we have a package to do that. All right, so what I want to show you is here, just to quickly, since we don't have much time, here's the one-way effect. It's probably hard to see, but all the one-way effects, there's two-way effects, and there's three-way effects. Okay, so you can see that mostly one-way effect is bigger. And that's what you would expect. It's called the sparsity principle.
So, because can you do the lasso on the interactive term as well, not just the
Yeah,
names?
the whole thing.
That's why.
Now there's a question about whether you should put some structure, but here we're just doing that. But you can see some of the interaction, the two-way, three-way interaction is bigger than say gender appears to have close to 0 one-way effect, but it pops up a lot here and it pops up a lot there. Okay, and let me give you one example here. So it's kind of interesting. So you can decompose the combination effect into a bunch of different marginal effects. So here, this is the effect of someone who's from Somalia and has 1 to 2 years of job experience relative to someone coming from India and no experience. So it seems there's a negative effect for this particular gene combination. You can decompose this into effect of Somalia versus India, and then effect of having the 1 to 2 years versus no experience. So there's a negative effect of being from Somalia. There's a positive effect of having a little bit of experience as opposed to none. And then there's the interaction effect. So that's beyond these two combination. There's something wrong about being from Somalia and having a little bit of experience relative to these India and none. Okay? And you can do this even in the three-way case. So that's why I think this is more intuitive. So let's look at the education, gender, and origin. So here someone has graduate degree, male, coming from India, with someone having same degree female from coming same country, and you see that the male Indian graduate degree is much more preferred than female. And then you might ask, why is that? Is that just because gender? Well, gender has on average almost no effect. We saw that one-way effect for the gender is very, very small. But something about coming from having the graduate and being male, and graduate by female also have very little effect. Okay, but what's happening is that male it's this one, right? Three-way interaction. So there's something special about this combination, these two combinations, beyond just being male female, or having graduate degree and male and female and so on. Right? So you can sort of decompose, thinking about. I mean, this is impossible when you have this many interactions. You can't just look at each cell. So you can sort of summarize, what's going on with many interactions. Okay, so just there's another one that I noticed, like high school male Germany, high school female Germany. Gender is the only difference, but it's a huge effect, right? And you ask why? Not gender in the high school, not really male and female, but this one. Right? There's something special beyond this lower order effect. Okay, so just to conclude, so interaction effects play an essential role. Thinking about causal heterogeneity, moderation, causal interaction. These are sort of main roles that interaction effects play. I want to sort of emphasize there are two different interpretations. Conditional effect, it's problematic in high dimension. It's still a valid question. And the interactive effect, the interpretation which we focused on. We introduced this new quantity, and it can be useful for interactive effect in the high dimension. Invariant to baseline condition, you can decompose the effect that I did at the end. And there's also the estimation challenges in high dimension, and this is true even when you're doing moderation. You can have lots of characteristics, and you might want to. So one way to do that is sparsity, and there might be other ways, but this is still, I think, it's a lot of development in the statistics literature.
Thanks, Kosuke.
Yeah.
We have a couple minutes. Questions?
Sort of I'm just trying to think through how I would use this if I,
Right.
I mean, I process it. But most of the variables you were talking about seem to be like sort of survey variables that are not experimental.
Right.
And so I just wanted to ask you if you envision this as something that could be used across a whole bunch of treatments that might interact in interesting ways, or are you more envisioning this as something that interacts in a survey context with one experimental treatment or a couple of experiments?
Right. I mean, conjoint is a very natural example because there's like gazillions of instructions. But you can imagine, especially if you're thinking about, from the policymaker's perspective, what's the most effective way to say get out the vote? You might want to vary messages. You might want to vary dose, how much messages you give. You might want to vary mode, like what method you use to contact voters, right? So you can imagine.
That would be a huge experiment, right? I mean,
Yeah.
to actually do.
1,300, and right.
You have
So
to
it
have-
could be huge. I'm not saying you should do it, but but right, you can imagine that if you have say 5 things you're not sure about, you want to vary because you want to find the best thing that works,
Yeah.
and that's this
In
basically.
a survey, you can have some interactive values that have no pieces that fit that, right? I mean, you can easily get, with the many interactions, that you have some categories that aren't filled. And you would
Right.
never, it would be weird to plan that way for an experimental set of treatments where you.
Right. But I think the original like Don and Aaron's paper had the number of males mirrorings being different. There are 3 messages. So I mean it's not this many, but there are few, if you take those, if you're interested in instructions, I mean you may be happy with the marginal effect, but if you're interested in what combination of those things lead to the highest increase in turnout, you might care about interaction. So, so it depends on what you're interested in. Certainly in medicine, this has individualized treatment regimes have been big. So they all want to figure out, they realize that same treatment doesn't work for everyone, sometimes kill some people. And you want to make sure that, they're giving the right thing. And maybe political scientists should worry about that too.
But that's still one treatment, right? It's like one treatment interacted with characteristics of the individual. That, I guess, it's never.
Oh, right. Yeah, well, yeah, so that's one, moderation more, right? But you can imagine, the cancer treatment, there's a dose and, there's how much interval you might, give to the patients. And there's all aspects that we are sort of, making the decisions. And if you want to experimentally figure out what are the best way to do it.
No, that makes sense.
Does this framework carry over to the first case you mentioned at the beginning, which is just treatment by covariate interactions?
It's harder, right? It's hard in part because there's going to be a correlation across covariates, because that's something we don't control. So nice thing about here is that if we assign the treatments, we can make them independent, and that makes the estimation a lot easier. So in theory, it's possible to bring it to that setting, but it's much harder because you have to take into account for the correlation structure. Here, it's that's the beauty of experiment is you can make it independent, so I can marginalize easily, much more easily than I don't have to think about conditional distribution. So, yeah.
Can I have maybe you said this and I missed it. If I use this method in a situation where I have a lot going on, then which of the standard causal interpretations of causal interaction do I end up with? That is, how do I interpret my results now in relation to how we normally think, the possible ways we normally think about interaction?
So here, the method that I'm proposing is limited to the interactive effect interpretation. So what's special about this particular combination beyond each separate part? But if your hypothesis is about conditional effect, that is, what is the effect of education given, your job experience, then you should, then by definition, you already sort of, you don't have to worry about this, what's the baseline.
So then this is only, you're saying that you would restrict recommending use of this, this way of doing it to situations where you are potentially interpreting, or you think that the causal interaction will have a genuine interactive effect.
Right, that's right. Yeah, that's right.
I think that's
because if you have conditional effect hypothesis, you're already, you know exactly what you should look for.